Bismillah ar-Rahman ar-Rahim. Alhamdulillah. Salatu wassalam ala Rasulillah. Yes, let's continue our discussion about chapter 10, and I'll start with 10.5, which is Dalton law. Dalton law of partial pressure. Dalton law of partial pressure. Good. And Dalton law says that it's very simple law, extremely simple law. It says that the P total of any gas is the sum of P1 plus P2 plus P3 plus P4 and so on and so forth. So in other words, the total pressure is the pressure of each gas by itself. And each gas, of course, we can apply the simple ideal gas law to find the pressure of each gas by itself. And the total pressure is the pressure of everything together. Okay, let's solve this problem. In 1 liter vessel contain 0.215 mole of N2 and 0.0118 mole of H2 gas. Determine the partial pressure of each component and the total partial pressure. Try to do it, and we'll discuss it further tomorrow. Good. Now, I will talk about now mole fraction. Mole fraction, very important, which we represented by Xi, is called mole fraction, is the number of mole of one gas I, compared to the total number of mole of all the gases in the container. The partial pressure is equal to the Ni, which is the number of moles of moles I, compared to Nt, which is total moles of all gases. Also, the mole fraction is equal to Pi, which is the pressure of pressure of gas I, compared to the total pressure. You have to know also these two laws. They are very simple and related to each other. Good. Okay. Calculate the mole fraction. Mole fraction. We want to calculate here Xi of NO or XNO gas cycle at room temperature that contain 6.022 mole N2 and in which the total pressure is 14.75. What should you do? Here you have the total pressure, which is equal to what? 14.75 atmosphere. This is equal to N total times RT over the volume V. Then you can calculate the N total. All right. If you know the N total, you can calculate the mole fraction of NO. Okay, so because you have the partial pressure of N2 gas, you can calculate if you know N total and you know N2, then you can calculate the partial pressure of N2, which is equal to 6.022 divided by N total, which we just calculated, and this will give you the partial pressure of N2. And since we have the total, the only two gases, then the mole fraction of N2 plus mole fraction of NO must be equal to 1, so we can calculate mole fraction of NO. Do it, and we'll discuss it further tomorrow. Good. Next, when we collect water, when we collect gases over water, like in this experiment, we are making gas, we're heating this compound, and this will produce oxygen gas, O2 gas. and the O2 gas will come and will be collected here over water. Then the gas will have pressure. Always the water will also have pressure, and that's why the P total is the pressure of O2 plus the pressure of H2O. The pressure of H2O is constant at certain temperature, and we can get the pressure of H2O from this table, which don't memorize any number of it. But if we have the experiment is done at room temperature, which is 25, then what will be the pressure of H2O only? It will be 23.8 millimeter Hg or torr. Clear? But if we do the experiment at 30 degrees, then the pressure will be 31.8 millimeter Hg. And so the pressure of H2O is constant at a certain temperature. Good. Now we are collecting H2 gas over water, and the room is 25 degrees C. So right away, what's the pressure of H2O? You can find it, which we just said a while ago. At 25 degrees, let's go back, and we'll find that's 23.8. So I'll put here 23.8 torr. I got this from the table, which is also here. Got it from the table. Okay. So if we have the total pressure is 0.967 atmosphere, then what will be the pressure of H2? It will be pressure total, which is 0.967, minus the pressure of H2O, but you have to keep the same unit. This is ATM and this is torr, so you have to change this one to ATM or change this one to torr to find the pressure of H2 only. Good. Okay, next, diffusion and effusion. Diffusion and effusion. And kinetic also. Application of gas theory. We're going to talk about now kinetic molecular theory of gases, and we're going to talk about molecular speed of the gas, which will represent by U. So this is the speed of any gas, and diffusion and diffusion. I'll define these. Next, kinetic molecular theory says that the gas is always in large distance from each other. They are not close to each other, and they are in constant motion. Constant motion. The gas is always moving. The most important thing, there is no repulsion or attraction between the gas molecules. So the gas molecules are moving freely with no attraction or repulsion between the molecules. And the most important word, that the gas molecules are always collide with each other. So they come like this and make collision together. This collision is elastic. Elastic. This, the meaning of elastic, it means that it does not release energy. Elastic means there is no loss of energy. So this is very important word. You have to understand it. Elastic collision, there is no loss of energy. Energy is transferred, but not lost. There is no loss of nitrogen in the collision. Good. From this, we will use a speed like this, which is the root mean square, speed, and we're going to call it from now on, which is the speed of all the molecules divided by the number of molecules. And instead of this thing, we're going to use URMS, which is root mean square. Root mean square, which is this one actually. This is the root mean square of URS. Good. Now, we know that energy is equal to half mu square, which is RMS square. Okay, which is this one. This week we're going to call it RMS, which is root mean square. But this is for one molecule. In order to have it for many molecules, I will have N, which is the number of molecules. If I want it for mole, then I'll use Na, which is 1 mole. What does Na means? Na is actually Avogadro's number. Na is Avogadro's number. Okay. Now, I also want you to know that the speed of the gas is proportional to temperature. As you increase the temperature, the speed of the gases also increase. And this proportionality, E is equal to 3/2 RT, where R here is the gas constant, but I will use the one with the units joule because I want it to be energy. So it is joule per mole Kelvin, which is actually 8.31. And since I am using 1, this means this equation is valid. And from this, if we derive, we can calculate the speed of the gas using this equation. I want you to memorize this equation very well. The speed of any gas is equal to the square root mean of 3RT over M. The 3 is constant. R is the gas constant, which is using joule mole Kelvin, and T is the temperature, and M is the molar mass, but I want it to be in kilogram, not in gram, and that's why you have to multiply the mass by 10 to the power minus 3 to make it kilogram. Okay, solve this problem. What is the URMS of chlorine gas at 30 degrees centigrade? Now, don't forget, when I say chlorine gas, I mean Cl2 gas. So the mass of Cl2 gas is what? 70.9 gram per mole, but since I want it to be in kilogram, I'll make it 10 to the power minus 3 kilogram per mole. Now use this mass in the equation, which is URMS equal to what? 3RT over the molar mass, but in kilogram, and that's why you should use this mass. Good, this is the answer. Next, if you want to compare the speeds, U1 over 2 is proportional, inversely related to the mass of 2 over 1. So 2 here, 2 up, and 1 here, 1 up. Memorize this equation, and this will give you the speed of these gases. Okay, solve this problem. Determine how much faster helium move on average than carbon dioxide. So I want the speed of helium over the speed of CO2. What's the equation? It's square root of molar mass of CO2 divided by molar mass of helium. Now, should I multiply it by 10 to the power minus 3 to make it kilogram? Or can I use gram? The answer is I can use anything, because whatever unit I have here, if it's kilogram and kilogram, or gram and gram, or even AMU and AMU, they will cancel each other. And don't forget, this is equal to square root of 44.01 divided by about 4, and this will give you the answer. Good. Now, what is diffusion? Diffusion means if you have two gases like this separated by this valve, what will happen if you open the valve? They will mix together. This is called diffusion. At the same time, if you have two compartments, one of it contains gas and the other one is vacuum, there is nothing in it, but there is a small hole, then the gas will escape from this compartment to the vacuum, and this is called effusion. We want to calculate the rate of diffusion or effusion, and this rate depends on what? On the speed. And so this is called Graham law, and the rate of effusion or diffusion is 1 over molar mass, or rate of effusion of 1 over rate of effusion of 2 is equal to square root of molar mass of 2 over molar mass of 1. This is the rate of effusion. But if you want to have time of effusion of 1 over time of effusion of 2, then this is equal to square root of molar mass of 1 over molar mass of 2. You have to be careful about this. Good. Let's solve this problem. Methane effuses approximately 2.4 faster than certain unknown gas. Which of the following could be the unknown gas? So rate of CH4 over rate of unknown equal to 2.4. So, and of course, this is equal to what? The mass of unknown divided by mass of molar mass of CH4, which is approximately 16. So calculate the mass U. And from the mass, you can tell which gas is the answer. Okay, which gas effuses faster, helium or argon? And how faster? Also solve this problem and answer it. Last question we have here, time. Now, time required for certain amount of helium gas to effuse 21.7 minutes. If it takes 72 minutes for the other gas, what is the unknown gas? What's the molar mass of the unknown gas? Now, since we have time of helium over time of unknown, this is equal to, since it's time, it's the molar mass of helium over the molar mass of unknown. And now, same thing, put the time, which is 21 here, 21.7, and this one is 72. And we know the mass of helium, which is about 4, so calculate MU. Okay? Okay, see you tomorrow, inshallah.